Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. In this lecture, we will discuss about Fermat's little theorem and we will see its application to primality testing, and we will also discuss about Carmichael numbers. So, let us begin with Fermat's little theorem. So, the theorem says that if p is a prime number and if a is an integer such that p does not divide a. So, this notation mean does not divide. In other words, a is co-prime to p, then the theorem says that a to the power p minus 1 is congruent to 1 modulo p, and this is true for every integer a which is co-prime to p. So, that is the Fermat's little theorem attributed to Fermat. Why it is called little theorem? Because we want to distinguish this theorem from another interesting theorem attributed to Fermat, which is also called as Fermat's last theorem. Okay. And this theorem also forms the basis for an interesting primality testing that we will see later on. So, this is the theorem statement, but before going into the proof of the theorem statement, let us see an interesting corollary of this theorem statement. So, assume for the moment that this theorem statement is true. Let us see an interesting corollary. So, the corollary is a to the power p is congruent to a modulo p for every integer a and prime p. Okay. And we can divide the proof into cases. So, the corollary is for every integer. Okay. It is not only for those integers a which are co-prime to p, right, whereas the Fermat's little theorem is strictly for those integers a which are co-prime to p. So, let us see the proof of the corollary first. Okay. So, we have two cases depending upon whether p divides a or not. Okay. So, the first case is when p divides a. So, if you have an integer a such that p divides a, then since a is divisible by p, any multiple of a is also divisible by p. So, hence a to the power p is completely divisible by p, and that means I can say that a to the power p gives you the same remainder which a gives you on getting divided by p, namely the remainder 0, because both a as well as a to the power p will be completely divisible by p if a is divisible by p. So, that proves that the corollary is true for case 1. Whereas, if p does not divide a, then we can apply the Fermat's little theorem. So, if p does not divide a, then that means the premise of the Fermat's little theorem is satisfied. That means, I can say that a to the power p minus 1 is congruent to 1 modulo p, and if that is the case, then if I multiply both the sides by a, I get the conclusion that a to the power p is congruent to a modulo p. So, that proves that the corollary is true even for the case when a is not divisible by p. Okay. Right. So, now let us come back to Fermat's little theorem and we prove it. Okay. So, we want to prove that you take any integer a which is co-prime to p, then a to the power p minus 1 is congruent to 1 modulo p. That is what we want to prove. So, the proof is as follows. So, you consider the first p minus 1 multiples of a, okay, namely 1 times a, 2 times a, 3 times a, and like that p minus 1 times a. All these are different multiples of a. The claim is that all these multiples of a, namely 1 time a, 2 times a, 3 times a, p minus 1 times a, when getting divided by p will give you distinct non-zero remainders. That means, whatever is the remainder that you will obtain by dividing 1 time a by p, call that remainder as R 1. Whatever remainder you obtain by dividing 2 times a by p, call that remainder as R 2, and like that whatever remainder you obtain by dividing p minus 1 times a by p, call that remainder as R of p minus 1. The claim is that none of these remainders are same. And of course, all of them are non-zero. Okay. So, the proof will be by contradiction. We will now prove this claim by contradiction. So, imagine you have two different multiples of A, say R times A and S times A, where R and S is R and S belongs to the set 1 to P minus 1, such that the remainder which you obtain by dividing R times A on dividing by P and the remainder that you obtain upon dividing S times A by P are same. Okay. The claim says that is not the case, but assume on contrary that you have two such different multiples which give you the same remainder. Now, if R times A and S times A are congruent modulo P, then as per the definition of congruence, I can say that R times A minus S times A is completely divisible by P. Okay. That means P divides R minus S times A. That implies that P has to divide R minus A, because as per the premise of my theorem statement, GCD of P and A is 1, A is co-prime to P, right. So, this is the premise of my theorem statement, right. You have a number P which is prime and P does not divide A, that means the GCD of P and A is 1. So, now you can recall one of the properties of divisibility that we had discussed in earlier lecture. If P is a prime which divides the product of two numbers and one of the numbers in the product is not divisible by the prime, that means the other number has to be definitely divisible by the prime, right. So, you have two numbers capital A, capital B. So, you can imagine R minus S as capital A and small a as B. So, we have P divides the product of big A and B, but P does not divide big B. So, that is possible only if P divides big A, and big A is R minus A, right. So, we get the conclusion that P has to divide R minus A, or in other words R and S are congruent modulo P. But if R and S are congruent modulo P, and since both R and S are strictly less than P, then the only way it is possible that R is congruent to S modulo P is that R is exactly equal to S, right. Of course, if R and S would have been outside the range 1 to P minus 1, then it might be possible that even though the value of R and value of S are different, but still they are congruent modulo P. But remember that R and S are strictly less than P, and if they are congruent modulo P, then that is possible only when R is equal to S. So, we arrive at a contradiction because we assume that R and S were different, right. So, R times A and S times A were different multiples, and that means R was different from S. That was our assumption, but we come to the conclusion that R is equal to S. So, that means whatever contrary statement we assumed is incorrect. That means this claim is true, right. So, we have proved this claim. Okay. Now, my claim is that if you multiply these P minus 1 multiples of A, okay. So, you have 1 time A, 2 times A, 3 times A, P minus 1 times A. If you multiply them, you will get one number. If you divide that number by P, you will get the same remainder which you will obtain if you multiply the numbers 1, 2, 3 up to P minus 1 and then divide the resultant value by P. That means, call the value on your left hand side as x, call the value on your right hand side as y. I am saying here that x will be congruent to y, okay. And this follows from your claim that we had just proved. This is because as per the claim, the various remainders which you obtain by dividing these P minus 1 distinct multiples of A, call them as R 1, R 2, R P minus 1. We have proved that all these multiple or all these remainders are non-zero and they are distinct. That is what the claim we have just proved. And all these remainders R 1, R 2, R p minus 1, they are the remainders obtained by dividing a value by p. So, the possible remainders that you can obtain could be 0 to p minus 1, but 0 is not a possible remainder as per the claim statement, right. We are not going to get a 0 remainder. That means, the only remainders that I can obtain are 1 to p minus 1, and at the same time they are distinct. So, that means definitely out of this p minus 1 remainders, one of the remainders is definitely 1. Out of this p minus 1 remainders that we are getting, one of the remainders is definitely 2. Out of this p minus 1 remainders that we are getting, one of the remainders is definitely p minus 1. So, that means remember the law of modular arithmetic says that if you want to multiply many numbers and then want to take modulo, you want to compute the remainder, then that is equivalent to saying that you reduce each of the numbers first modulo the same modulus and then multiply them. So, I can say that instead of, so I can say that the the value of x modulo p will be the same as multiplying the remainders r 1, r 2, r of p minus 1 and then taking modulo p. And I know that r 1, r 2, r p minus 1 are the values 1 to p minus 1 in some order, right. R 1 may not be exactly 1, R 2 may not be exactly 2, R of p minus 1 need not be exactly p minus 1, but I know that the remainders 1 to p minus 1 occurs exactly once among these p minus 1 remainders. So, that is why I can say that the product of these p minus 1 remainders is congruent to the product of 1, 2, 3 up to p minus 1 modulo p, okay, which is y. So, that means now I can say the following. So, if you see the expression x, the value a is appearing p minus 1 times. So, I can take out a to the power p minus 1 outside, and then if I collect the product of 1 2 up to p minus 1, that will be p minus 1 factorial, whereas in my right hand side, namely y, I have p minus 1 factorial, because that is the product of 1 2 up to p minus 1. So, that means I can say that a to the power p minus 1 times p minus 1 factorial is congruent to p minus 1 factorial modulo p. Now, what I will do is the following. Let me multiply both the sides of this above equation by the multiplicative inverse of p minus 1 factorial modulo p. Now, you might be wondering, what is the guarantee that the multiplicative inverse of p minus 1 factorial modulo p exists? So, recall we discussed in one of our earlier lectures that multiplicative inverse of a value modulo some modulus n exists if and only if that value is co-prime to the modulus. So, that means p minus 1 factorial's multiplicative inverse will exist only if this condition is true, because your modulus is p and this is the value x whose inverse you want to find out. Not let us not call it x, because I have already used x for something else. So, call this value as z. So, my claim is that the value z, which is p minus 1 factorial, is indeed co-prime to n, and it is very simple to prove that. Okay. I am not going to prove that for you, I leave that as exercise for you. Okay. So, since the multiplicative inverse of p minus 1 factorial exists, if I multiply both the sides by the multiplicative inverse of p minus 1 factorial, then this p minus 1 factorial when multiplied by its multiplicative inverse will give me 1, and 1 multiplied by a to the power p minus 1 will give me a to the power p minus 1 in the left hand side, whereas in the right hand side when I multiply p minus 1 factorial with its multiplicative inverse, I get 1. So, I get the conclusion that a to the power p minus 1 is congruent to 1 modulo p, which proves my Fermat's little theorem. Okay. So, this is the Fermat's little theorem, which says that every integer a which is co-prime to p satisfies the condition that a to the power p minus 1 is congruent to 1 modulo p. And I have a corollary of this theorem that you take any integer a which need not be co-prime to a, it satisfies the property that a to the power p is congruent to a modulo p. So, now let us see some of the applications of this theorem. It has this Fermat's little theorem has got tremendous applications. So, let us see how exactly we can use this theorem to compute the value of some expressions modulo some modulus, which is a prime number. Okay. So, your modulus p here is prime, and say I want to compute the value of 7 to the power 222 modulo 11. Okay. Of course, you can write down a computer program and compute the value of 7 to the power 222 modulo 11, but I want to do it very quickly using my paper and pen and using Fermat's little theorem. So, what I can do here is the following. If I substitute a equal to 7 and p equal to 11 in Fermat's little theorem, then I see that the condition of the Fermat's little theorem is satisfied, because indeed GCD of 7 and 11 is 1, namely 7 is co-prime to 11, because the GCD of 7 and 11 is 1, and hence I can say that 7 to the power 10 will be congruent to 1 modulo 11. That means, if you divide 7 to the power 10 by 11, you will get the remainder 1. Now, I can rewrite 7 to the power 222 as follows. I can treat it as 7 power 10 modulo 11 multiplied by 7 power 10 modulo 11 multiplied by 7 power 10 modulo 11, and then finally 7 square modulo 11, and then everything modulo 11. So, basically what I am doing here is that 222 can be rewritten as 220 plus 2, and now this 220 can be written as 22 times 10, and then you have 2 anyhow. So, this 7 power 222 I have splitted it into many blocks of 7 power 10, 7 power 10, 7 power 10, namely 22 blocks, and then finally I will be left with 7 power 2. And then since I have to do, or I have to compute everything modulo 11, I can take modulo 11 with each block of 7 power 10. Again, this comes from your rules of modular arithmetic. Okay. Now, I know that 7 power 10 modulo 11 will give me 1. So, each block of 7 power 10 modulo 11 will give me 1, 1, 1, 1, 1. That means, I will get 1 multiplied with each 1 multiplied with itself 22 times, which will be given me again 1, and then that will be multiplied with 7 square modulo 11, and 7 square modulo 11 is 5. And then I can say that 1 into 5 is 5, 5 modulo 11 is 5. So, you can now see that I do not need to write any complicated program, or I do not need to do any sophisticated computation. I can simply apply the Fermat's little theorem, and so conveniently I can compute the value of 7 power 222 modulo 11. Okay. Now, as I said at the beginning of the lecture, Fermat's little theorem also forms the basis of a very interesting primality testing algorithm. We will not be seeing the full primality testing algorithm, but we will see a part of it. So, this is the statement of the Fermat's little theorem, which says that if you have a number p which is prime, then any integer, and if you have an integer a which is co-prime to p, then for every such integer a, the value of a to the power p minus 1 is congruent to 1 modulo p. So, now the question is, can I use the above theorem statement to check whether a given number n is prime or not? Of course, the number n has to be odd, because if I give you n equal to n equal to 2, you can easily verify, you can easily conclude that it is a prime number, because that is the only even prime number. But other than that, all prime, if at all n is a prime number, it has to be odd. So, now you are given an odd prime number, it might be an arbitrary large prime number, and you want to utilize Fermat's little theorem to verify whether the given number n is prime or not. So, the idea here will be that I will pick some arbitrary integer b such that b is co-prime to n, and then I will check whether b to the power n minus 1 is congruent to 1 modulo n or not. I do not know whether n is prime or even prime or composite, I have to check. So, what I am saying is, to verify whether the given n is prime, pick some random integer b which is co-prime to n, and then check whether for the b that you have chosen, b to the power n minus 1 is congruent to 1 modulo the given n. Now, you will get either the answer yes or no. If you see that b to the power n minus 1 is not congruent to 1 modulo n, then you can simply declare that the given number n is composite, because that comes from the contrapositive of your Fermat's theorem, right. So, the Fermat's theorem is that if you have a number a, right, which is co-prime to p, and if p would have been prime, then a to the power p minus 1 will give you 1 modulo p. So, the contrapositive of that will be, if you have a number a which is co-prime to p, and if a to the power p minus 1 is not congruent to 1 modulo p, then that implies that a is then that implies that p is not prime, even though a is co-prime to p. That is a contrapositive, and that is what precisely we are using here. But what if b to the power n minus 1 is congruent to 1 modulo n? Can I declare my n to be a prime number? Well, that is the problem with this primality testing. Even if b to the power n minus 1 is congruent to 1 modulo the given n, you can't necessarily declare your number n to be a prime number. So, here is a counter example. So, imagine your given n is 341, which is an odd number and which is not a prime, it is a composite number, because the number 341 has factors 11 and 31. Now, suppose when you run this primality testing algorithm for n equal to 341, you pick your b to be 2, right. So, indeed GCD of 2 and 341 is 1, and it also turns out that for the given b that you have chosen arbitrarily, b to the power n minus 1 is indeed congruent to 1 modulo the same n. So, you can't, even though this condition is true, the condition of Fermat's little theorem is true, you can't declare your n to be prime, because the value n 341 is indeed composite. So, that is why this primality testing algorithm is not a robust algorithm, robust in the sense you can't trust the answer. If the answer is composite, yes, you can trust it, but you can't trust the answer that n is prime. It may be the case that even though your value n is not a prime number, the condition for Fermat's little theorem is satisfied. So, now you might be wondering that why can't I do the following? It might be possible that I have chosen a bad b with respect to my given composite number n. What if I choose a good b which is co-prime to n and for which the Fermat's little theorem condition fails? In that case, I can declare that my n is not a prime number. Why can't I do that, right? However, it turns out that even if you do so, your primality testing algorithm will fail, because there are some very interesting numbers which are called as pseudo primes and Carmichael numbers, which will cause your primality testing algorithm to fail for the case when your n is composite, but you are not able to detect that. Okay. So, let us first define pseudo primes and then we will use it to define Carmichael numbers. So, imagine you are given positive integers b and n and say your n is composite. Okay. Now, if it turns out that b to the power n minus 1 is congruent to 1 modulo n, then I will call my n to be a pseudo prime to the base b. Why I am calling it pseudo prime? Because it is a false prime. In the sense, even though my n is composite, it satisfies the condition of Fermat's little theorem with respect to the integer b. That is why I am calling it base b, because b is appearing in the base and n minus 1 is appearing in the exponent. So, for instance, the counter example that we just saw in the previous slide shows us that the value n equal to 341 is a pseudo prime, it is a false prime, because it is actually a composite number, but still it satisfies the condition of your Fermat's little theorem with respect to your base b equal to 2. So, now as I said earlier, you might try to run the you might try to run the primality testing algorithm with respect to several bases for a given number n, with a hope that indeed if your value n is composite, you hit upon some base for which the condition or the conclusion of Fermat's little theorem is not satisfied. So, what we are doing here is we are now proposing a modified primality testing algorithm, where instead of picking one base b, which we had done earlier, we are now randomly picking many bases, say m number of bases b1 to bm, each of which is co-prime to your given number n. You want to check whether the number n is prime or composite. Okay. And now you check whether the condition of Fermat's little theorem holds for each of the bi's and given n. Namely, you check whether b1 power n minus 1 is congruent to 1 or not, b2 power n minus 1 is congruent to 1 or not, and bm power n minus 1 is congruent to 1 or not. Even if for one of the bases bi the condition of the Fermat's little theorem does not hold, you can very confidently declare that your number n is composite. But what it so happened that for each of the m bases which you have randomly chosen, the condition of the Fermat's little theorem is satisfied. Can you declare your given n to be a prime? Unfortunately, we can't do that, and there are some wonderful numbers, very interesting numbers, which are called as Carmichael numbers, which will actually cause your modified primality testing algorithm to fail. So, what exactly are Carmichael numbers? So, they are composite numbers which are pseudo primes with respect to every base that you can think of. So, you pick any base b or any integer b which is co-prime to your number n, still the condition of Fermat's little theorem will be satisfied for them. That means, b to the power n minus 1 will be congruent to 1 modulo n. Okay. It does not matter whether your base b is b1, b2, you pick any base, that base power n minus 1 will be congruent to 1 modulo n. Okay. Namely, it will be a pseudo, namely your n will be a pseudo prime with respect to every base that you can think of, right. So, that tells you that if you now input a number n which is a Carmichael number, then definitely this primality testing algorithm will fail, because it does not matter how many bases you pick. Okay. Each of them may be co-prime to your n, fine, but still this condition will hold, and then you will be in a dilemma whether I should safely declare n to be a prime or not. If you declare n to be prime, then that is a false conclusion, because actually your number n is composite, right. So, that is why the primality testing algorithm based on Fermat's little theorem is not a foolproof test, and we need to make additional test in the modified primality testing algorithm to get a foolproof primality testing algorithm, whose details I am not going to discuss. So, now you might be wondering, do Carmichael numbers indeed exist, and if they exist, are they finite or are they infinite in number? So, indeed it turns out that we have lots of Carmichael numbers. In fact, the study of Carmichael numbers itself is a very interesting research topic in number theory. So, let me give you an example of a Carmichael number. So, my claim is that 561 is a Carmichael number. So, you can see that 561 is not a prime number, because I have written down its prime power factorization, namely you have 3 factors p1, p2 and p3 for the value n equal to 561. Now, I want to prove that the value 561 is indeed a Carmichael number. For that, I have to prove that it is a pseudo prime with respect to every base. You think of any base b which is co-prime to your n. I will show that b to the power n minus 1 is congruent to 1. Okay. So, this is my goal. I am not focusing on the value of the base p. The only thing that I know is that it is co-prime to your n, namely 561. So, how do I prove that b to the power 560 will be indeed 1? So, since I know that the GCD of b and 561 is 1, I can imply that individually b is co-prime to each of the prime factors of my n. So, b will be co-prime to 3, b will be co-prime to 11 and b will be co-prime to 17. It is very easy to prove this implication, because if any of these implications is false, say for instance, if GCD of b and 3 is not 1, that means there is some common factor for b as well as 3. So, then I can come to a contradiction that GCD of b and 561 is not 1. Okay, that is as simple as that. Now, since b is co-prime to 3, b is co-prime to 11 and b is co-prime to 17, I can do the following. I can rewrite b to the power 560, and my goal was to show that b to the power 560 is congruent to 1. So, b to the power 560 I can rewrite as b square and then whole raised to power 280. Okay. And b to the power 560 will be congruent to 1 modulo 3. Why so? Because b to the power 560 modulo 3 is same as b square whole raised to power 280 modulo 3. But I know that since b is co-prime to 3, I can apply the condition of Fermat's little theorem. So, I can treat 3 to be my prime p, and I can treat b to be a number which is co-prime to 3. So, that gives me that b to the power 3 minus 1, namely 2, is congruent to 1 modulo 3. So, now if b square gives me the remainder 1 modulo 3, then b to the power 560 will give me this much remainder. So, I have basically divided b to the power 560 into several blocks of b square, b square, b square, namely 280 blocks, and each block of b square gives me the remainder 1 modulo 3. So, basically I get 1 multiplied to itself 280 times, which will be 1 modulo 3. In the same way, b to the power 560 is congruent to 1 modulo 11, and this is again because 11 is a prime number and b is co-prime to 11. So, I can say that from Fermat's theorem, Fermat's little theorem, b to the power 11 minus 1, which is 10, is congruent to 1 modulo 11, and hence b to the power 560 can be rewritten as 56 blocks of b to the power 10 modulo 11. Each block of b to the power 10 modulo 11 will give me 1 as the remainder, and 1 multiplied to itself 56 times will give me the remainder 1. And in the same way, b to the power 560 will be congruent to 1 modulo 17, because again I can apply the Fermat's little theorem here. 17 is a prime number, b is co-prime to 17. So, from Fermat's little theorem, b to the power 17 minus 1, namely 16, will be co-prime to 1 modulo 17. So, I can rewrite b to the power 560 as 35 blocks of b to the power 16 modulo 17. Each block of b to the power 16 modulo 17 will give me remainder 1, and hence I will get 1 multiplied to itself 35 times, which will give me the remainder 1. So, that means b to the power 560 is congruent to 1 modulo 3, b to the power 560 is also congruent to 1 modulo 11, and b to the power 560 is also congruent to 1 modulo 17. So, now recall the CRT helping lemma. So, let me rewrite the CRT helping lemma. So, there you had n modulus and n number of modulus which are pairwise co-prime, and you have two values a and b which are congruent to each other with respect to all the moduluses. So, you have a congruent to b modulo m1, a congruent to b modulo m2, and like that a congruent to b modulo mn, and it is given that all this n modulus they are pairwise co-prime. Then the conclusion is that a is congruent to b even modulo the bigger modulus, which is the product of all the individual moduluses. So, that was the CRT helping lemma. So, now I can treat my capital A to be b to the power 560, I can treat my capital B to be 1, and I have 3 moduluses here, m 1 being 3, m 2 being 11 and m 3 being 17. So, A is congruent to B modulo m 1, A is congruent to B modulo m 2, A is congruent to B modulo m 3, and hence I can say that A is congruent to B modulo the product of m 1, m 2, m 3. The product of m 1, m 2, m 3 is nothing but 561. A is anyhow b to the power 560 and b is 1. So, I have shown that b to the power 560 is indeed congruent to 1 modulo 561 without even knowing the value of b. So, b was an arbitrarily chosen base such that it was co-prime to your number n. So, that shows that the value 561 is indeed a Carmichael number. So, that brings me to the end of today's lecture, and with that I also finish my discussion regarding the number theory. As I said earlier, that number theory in itself is a very interesting subject, and we can have a full fledged course just on number theory, but we want to get just a flavor of discrete flavor of number theory that is required in the context of discrete maths and computer science. Thank you.